welcome to Sunil's tutorial. I'm Sunil Nurwani and today we'll be doing this chapter called as electromagnetic induction. Let's start. Now let's first try to understand what is electromagnetic induction. Let's consider a coil. Connect a galvanometer to the coil, right? Place the north pole of a magnet at one end of the coil. Okay. Now move this magnet to the other end of the coil and then bring it back. Move the magnet to the other end of the coil. Move the magnet to the other end of the coil. You have coil. Galvanometer. Move it to the other end of the coil. South, north. You already moved it here. Now move it back to the original position. Move it back to the original position. Right? It is observed that as I move the magnet on the coil from one end to another end and bring it back, the galvanometer shows some deflection. The galvanometer would show some deflection only when an EMF is induced in the coil, when an EMF is produced in the coil. That means if I move a magnet on a coil, certain amount of EMF is generated. Since this EMF is generated without any physical contact, therefore this is called as induced EMF. Fine, do we get this thing here? Let's write this experiment down. Magnet and coil experiment. Right? Coil of the wire of a wire is connected to a sensitive galvanometer Coil of the wire is connected to a sensitive galvanometer and a strong magnet is held near the coil. Right? Now, it has been found out that the galvanometer does not show any deflection when the magnet is held steady near the coil. The galvanometer does not show any deflection when the magnet is held steady near the coil. Right? But if the magnet is suddenly moved towards the coil, the galvanometer shows a momentary deflection. But if the magnet is moved towards the coil, while the galvanometer shows momentary deflection. Right? Now, if the magnet is moved away from the coil, the galvanometer shows a similar momentary deflection. So whether I move it towards the coil or I move it away from the coil, the galvanometer is going to show same deflection. Right? If the same magnet is moved away from the coil, the galvanometer shows similar momentary deflection. Momentary deflection. Right? From this, what we understand is that also if the magnet is, if I do the experiment in reversing, if the magnet is kept fixed and the coil is moved, you get similar results. Also, if the magnet is kept fixed and coil is moved, similar results are obtained. Right? That means in the above procedure, what we understand is that we have kept the north pole pointing towards the coil. If the south pole is kept pointing towards the coil, you get a similar deflection but in opposite direction. Right? In the procedure described above, the north pole of the magnet was kept pointing towards the coil. Right? Now instead of that, if instead the south pole is kept pointing towards the coil, if the south pole is kept pointing towards the coil, so, the result obtained are similar, but the only difference is that the deflection is reversed. The results obtained are similar, right, with only difference that the deflection is reversed. Right? Now, from this experiment, what we understand is that when a magnet is kept steady near the coil, there is no change in the magnetic flux linked with the coil. But when the magnet is moved towards the coil, the magnetic flux linked with the coil increases, and when it is taken away, the magnetic flux linked with the coil decreases. Right? So there is a change in the magnetic flux, number of lines. Magnetic flux, the number of lines produced, and this change in magnetic flux that produces an EMF in the coil, and that is the reason why current begins to flow. So try to understand this. When the magnet is kept steady near the coil, there is no change in the number of magnetic lines. Now as I move the magnet towards the coil and move it away from the coil, the number of lines of force change, the number of magnetic flux changes. Now since the number of magnetic flux changes, this change of magnetic flux produces an EMF which causes a current to flow. This EMF which is produced is called as induced EMF, and the current is called as induced current. Fine. The faster I move the magnet, more will be the EMF and more will be the current that will be produced. And this phenomenon of production of EMF in the coil by changing the magnetic flux is called as electromagnetic induction. So what is electromagnetic induction? It is nothing but it is the production of EMF in the coil by changing the flux associated with the coil. Right? So here what we see is that when the magnet is moved, when the magnet is moved, the magnetic flux linked with the coil changes. The magnetic flux linked with the coil changes, right? And this change in magnetic flux produces EMF. This change in magnetic flux produces EMF, right? Electromotive force in the coil. That's the reason why EMF is produced in the coil, and this EMF is called as induced EMF. This EMF is called induced EMF. Fine. So this phenomena of production of induced EMF in the coil by changing the magnetic flux associated with it is called as electromagnetic induction. So how do I define? Definition of electromagnetic induction: the phenomena of production of induced EMF in a coil by changing the magnetic flux associated with the coil is called electromagnetic induction, EMI. Sorry, right? So do we understand what is EMI? But here we have a problem. Who will hold the magnet? Who will move the magnet? That's going to be a big problem. Let's try to come up with a solution for this. Instead of taking one coil, let us take two coils. Let's keep the two coils close to each other. Connect a galvanometer to one of the coil, and to the other coil connect a battery and a switch, right? Positive terminal of the battery and switch A. Let's call this winding as A and this winding of the coil as B, right? Now the first winding where you have the DC EMF connected, that is called as the primary winding, and the other winding, that is B, where you have the galvanometer connected, that is called as secondary winding. So this is my primary winding, this is primary, and this is called as secondary. Fine. Now, as soon as I close the switch, if the switch is closed, the instant when the switch is closed, the primary circuit is complete and the galvanometer shows a deflection, right? That is when a steady current flows through the, you have, as I close the switch, you will have a steady current flowing through the coil, right? When I open the switch, the current will stop, right? Now when current flows through a coil, it produces a magnetic field. So when current flows through the primary windings, it will produce a magnetic field around the primary winding. Coil B is in the magnetic field, right? So therefore a magnetic flux will be produced even in coil B. When I switch the current off, there will be a change in magnetic flux. Then again when I switch it on, magnetic flux will be produced. When I switch it off, there will be a change in magnetic flux, it will come to zero. So this change in magnetic flux, there will be a change in magnetic flux, and we said that whenever there is a change in magnetic flux, an EMF is going to be produced. So if I just plug the switch on and off, automatically an EMF will be produced. Fine, do we get this thing clear? Let's write this down. So you have, in this experiment, let's try to understand how flux is produced without moving the magnet. I can say that at the instant the primary circuit is closed. Primary circuit is closed means the switch is turned on. The primary circuit is closed. The galvanometer shows momentary deflection. Right? Now, when steady current starts flowing through the primary, no deflection is there in the galvanometer. When steady current flows through primary, when steady current flows through primary, there is no deflection in galvanometer. The deflection is the moment I plug the switch on, right? Now the instant when the primary circuit is broken means the switch is turned off, once again the galvanometer shows a momentary deflection. At the instant the primary circuit is broken, the galvanometer once again shows momentary deflection. Right? Now, in the above procedure, what we understand is that the instant the primary circuit is made, current flows through the primary. The current in the primary grows from 0 to maximum. Hence, magnetic flux round the primary increases, and the secondary coil is placed in the magnetic field, and therefore the magnetic flux linked with the secondary also increases. This results in an EMF, which is induced in the secondary, which causes the galvanometer to show deflection. As the current in the primary reaches a steady state, there is no change in the flux, and therefore the galvanometer after that does not show any deflection. The instant when I switch the plug off, when the primary circuit is broken, the current in the primary reduces, therefore the magnetic flux associated with the primary reduces, which causes a reduction in the magnetic flux induced in the secondary, which again causes a current to flow. So from here what we understand that a change in flux produces EMF. It is not the constant flux that produces EMF, but it is the change in flux that produces EMF, right? On the basis of this, what we understand that Faraday, these experiments were done by Faraday. Faraday proposed two laws. Those are called as Faraday's laws of electromagnetic induction. He said that whenever there is a change in magnetic flux associated in a coil, an EMF is induced in the coil. If I change the flux, EMF is going to be produced, and the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. It does not depend upon how many batteries you are connecting. It depends upon how many times you are going to plug the switch on and off. That will tell you how much EMF will be produced. Right? Let's write this down. At the instant the circuit is made, at the instant the primary circuit is made, current in the primary grows from 0 to maximum. Current in primary grows from 0 to maximum. Hence, the magnetic flux around the primary increases. Magnetic flux around the primary increases, right? And the secondary coil is placed in the magnetic field. Secondary coil is placed in this magnetic field. Right? Hence, as a result, an EMF is induced in the secondary coil and the galvanometer shows momentary deflection. As a result, an EMF is induced in the secondary and galvanometer shows deflection. Momentary deflection. Right? Next. This is when you plug the switch on. Next. As the current in the primary reaches a steady value, as the current in primary reaches a steady value, there is no change in flux. There is no change in flux. Constant amount of flux is produced. There is no change in flux linked with the secondary. Hence, the galvanometer shows no deflection. Hence, galvanometer shows no deflection. Right? Third, when you plug the switch off, at the instant when the primary circuit is broken, at the instant when primary circuit is broken, at the instant when the primary circuit is broken, the current in the primary decreases. Current in primary decreases, right? And therefore there will change in magnetic flux. Therefore there is a change in magnetic flux. As the current decreases, there will be a change in the magnetic flux linked with the primary and hence with the secondary. Linked with primary and hence in the secondary. Right? So thus you have a change in the magnetic flux in the primary and secondary. As a result, an EMF is induced in the secondary and the galvanometer shows deflection. As a result, an EMF is induced in secondary and the galvanometer shows deflection. Right? So thus from this experiment what we conclude is that any change in flux associated with a coil produces an EMF in the coil. Therefore I can say that any change in flux associated with the coil produces an induced EMF in the coil. So now we understand why an EMF is induced in the coil, how potential difference is produced, right? Now, let's write Faraday's law based on this. Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. His first law states that whenever there is a change in magnetic flux associated with the coil, whenever there is a change in magnetic flux associated with the coil, an EMF is induced in the coil. EMF is induced in the coil. So that's when you change the magnetic flux in a coil, you will have an EMF in the coil, and the magnitude of the induced EMF, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. Change of flux. Right? These are two Faraday's laws. Now on the basis of this, I can therefore say that magnetic flux linked in a coil changes with time. Magnetic flux linked, if the magnetic flux linked with a coil changes with time, and EMF is going to be produced. So I can say from Faraday's first law, I can say that if phi is the flux, right, and E is the EMF, then I can say EMF produced in a coil is directly proportional to the rate of change of flux, first and second law. Rate of change of flux. So he therefore said that E is equal to d phi by dt. E is directly proportional to d phi by dt. Now, the unit of EMF is volt and magnetic flux is Webers. As such, the constant of proportionality in the above relation is equal to unity, and hence I can say unit of EMF is volt and unit of flux is Webers. Both are equal units, hence I can say that constant is going to be equal to unity. Since both the units, that is of EMF and flux, are equal, Therefore, I should have had E is equal to K times d phi by dt, right? Since the value of volt and the units of EMF and flux are same, therefore I can say Webers per unit time will give you volts only. Hence, the constant will be unity, and therefore I can say E is equal to d phi by dt, since K will be equal to unity, right? So this is your mathematical formula for EMF induced in a coil, right? The above relationship shows Faraday's laws of magnetic induction. Both the laws are put forward in this one equation, right? Now, on the basis of this, you had another law that was formed, which was called as Lenz's law. Right? Now, according to Lenz, he said that the direction of the induced EMF is such that it opposes the change in the magnetic flux. So, if flux is in a particular direction, then EMF will be produced in opposite direction. What he observed was that the direction in which you have flux and the direction in which EMF is produced are opposite to each other. So, the flux induced will be such that it will try to oppose the change, the EMF induced will be such that it will try to oppose the change in flux. So according to Lenz, he said that the direction of induced EMF is such that it opposes the change in magnetic flux. That means the direction of the flux and the EMF is going to be opposite. Hence, if I combine Faraday and Lenz's law, thus Faraday and Lenz's law together can be written as E is equal to negative d phi by dt. E is equal to d phi by dt. Why negative sign? The negative sign says that the direction of the EMF and flux are opposite to each other. Fine, do we get this thing clear? Question. Why is it that the direction of the induced EMF and flux are opposite to each other? Now, let's try to understand this, people. In a coil, let's consider the first experiment. In the coil in the magnet experiment, when the north pole, let's see this, in the coil in the magnet experiment, when the north pole of the magnet was brought near the coil, the current induced in the coil was due to the change in the flux linked with the coil. I have north pole here. Now as I move, why will a current be induced in this coil? The current will be induced because there will be a change in magnetic flux, the number of lines at a particular place. In this case, the direction of the induced current will be such that it will behave as a magnetic dipole with its north pole pointing towards and approaching the north pole. As I move this magnet, what kind of current will be induced here? It will be a current that will be induced due to north pole. So it will behave like a north pole, right? Hence it will tend to repel the north pole. The current induced here is going to be because of the north pole, hence it will behave like a north pole. And we know that like poles repel each other. We know that like poles repel each other, and that is the reason why you will have an induced EMF which will be of reverse polarity. Similarly, if I look at this direction here, if I move the south pole away from the coil, then at the first end of the coil, you will have an EMF that will be induced due to the south pole. Hence, the induced EMF will behave like a magnetic dipole having south pole. Since we know that like poles repel each other, therefore it is going to oppose this movement. Fine, do we get this thing here? So, do you understand the basis of Lenz's law? Why does he say that the direction of the induced EMF is such that it opposes the change in magnetic flux? Fine, do we get this thing clear? Now, let's move on ahead. Okay, we'll do one thing. We'll stop this here for the day. We'll take up the next topic in the next lecture. Thank you very much.